Welcome. Uh, we will learn how to do linear regression using least square method. So the objective by the end of this lesson, you should be able to perform linear regression using ordinary least squared method and evaluate the model fit. Remember, like for example, like model fit, you can like R square, for example. Then understand multivariable regression. I will show you also an example of a multivariable regression and I will discuss how I solved it. And then whether like linear or non-linear, we should also describe the assumption of linear regression. Sorry, whether like single variable or multivariable, we will assign the assumption of linear regression, including like linearity, independence, like so that like your data is linear, your data is independent, your data has a constant variant and normality of the error, and your error or residual follow a normal distribution. So these are the assumption that you need to satisfy to be able to have a meaningful like your linear regression result will be meaningful. So we will also look at this assumption and we will not get to in the implication of violating this assumption, but I will guide you, like if you want to read and learn more about this, I will guide you to some references to how to read, but we'll just look at this assumption. So that basically before you use linear regression, you make this check on your data, and accordingly you can make some meaningful inference and conclusions based on your regression model. Okay, so let's just start by using the least squared method, or basically we will look at it's called like also ordinary least square, OLS, ordinary least square. So the idea is like you are fitting a straight line to a set of paired observations. So you have a paired observation like x1 and y1. So here, so at x is equal to 0, I got like this y1. Uh, so this is this observation. At x is equal to whatever, I got like this y2 here. So like this is my data. So this is like a paired. So this is like x1, y1. This would be like my x2, y2. That would be my x3, y3, and so on, and so forth. So you have like these pairs of data to xn, yeah. And these pairs of data, you want to find the line that will fit this data such that you will minimize the error or like the residual. So what is the error or what is the residual? Basically, this is the residual. So the distance between like your model. So my model is here and my data is here. The distance between my model and my data, this called the residual. This called the residual. So you see this residual here is very small. The residual here probably is the highest. So this data point has the highest residual. This residual here is also very high. So basically I want to keep like finding like, is it this line or this line or this line or whichever line? What is the line? What is the slope and intercept of the line that will make like these residual as like these all these residual as small as possible? Yeah, so it's called like least square method. So here in so the simplest model you can fit to this, as we discussed before, is like a linear model, an equation of a straight line. So basically, what this linear model will be. So here I have this is like my intercept, and this is my slope. So here, this is the intercept. So whatever it will be like here, this is the slope of my line. So that would be like something here. And whatever that like my independent variable cannot explain from my dependent variable, that would be the error. So that would be the part, like, so this model can explain some part of this y, And that remaining part that cannot be explained by this model, that would be my error, or that would be my error. Okay, so basically, so that would be the intercept, that would be the slope, and that E would be like the error or the residual. So if I want to find a model for my error, like an error model, like or an error for my residuals, that would be what? So that would be basically like this guy, yeah, like this guy minus like my observed, my minus like my model here. That would be like the error, like the model for my residual. So if I want to model this residual, I mean, this is just one way of modeling this. Uh, Based on like certain assumption, like the assumptions that I said, like of linearity, constant variance, independence, so I can model my error as such. Yeah. So that would be my how I could model this residual. Basically, yeah, it is like you just bring this guy here, and that would be. But again, this could change. Like if my constant variance or independence or linearity assumption are different, this residual model ours could be also different. But so that could be like my model, and so this is like the error model. E represents the discrepancy between the true value of y. So this is like the true value of y and the approximate value predicted by the linear equation. So that basically that's the true value here, and that is the value predicted by the model here. That would be like your true value here, and that would be the value predicted by the model. And again, this definition is good whether you are like for linear or nonlinear regression also. So that see like the true value is here, and what's predicted by model here is very small. So here that's the true value of y. That's like your y here, and that is what is predicted by the model. Okay. Again, if you are wondering, so here uh, the model, the linear model, for example, that I fitted to this data has a slope of, this is an example of 1.7. So that is my A1 and has an intercept of 3.28. That is my A0. Yeah. And the model that I use to generate like this random data from it has like slope of 2 and intercept of 1. Okay, that is a model that I use to generate this data from, and it has like a big variance. Okay. Uh, I'm not sure if this is true. I have to double check this, but I mean, this could be either 1 or 3 because I use like a lot of models, so that could be just an error when I copy this. But doesn't it makes no difference whether this is 1 or this is 3. It really makes no difference. Okay, but because that's just like here, I'm just like this is just like for illustration purpose. Yeah, and usually in real life we don't know this equation. In real life, we just collect this data, and if we know that this data is following like linear processes, then we fit a linear model to it. Okay, so now the question is like how to find this line, how to find this like best fit line, like this best fit line, like this best fit line, like how to find this best fit line. Well, there is a way for doing this because so the fit of the best line, we can be estimate like basically like what are we trying to do here? Like basically we are trying to estimate the value of A1, yeah, and A0. So what, like you keep playing with this value with the slope and intercept so that you would minimize the residual. You would minimize like this E. So basically, like this can be just formed as an optimization problem. So what is the value of A and A naught that will minimize my E? So basically, that is how you can solve this one. So you estimate the intercept, you estimate the slope that minimize the E, the sum of the squared residual. So here So this would be called like the SR, or the sum of the square residual. So I get like all my residual. And again, why do we square them? Remember, why do we square them? Because if we just sum them, like this guy will cancel away with this guy. I mean, these two guys will cancel away with this guy. So my residual or my error would be 0. But when I square them, I will get rid of this problem, and I will also exaggerate the error. Yeah, I will be inflating the error to avoid avoid fitting errors. Yeah. Okay. So, and what is this guy? Remember, like this guy, this is my observed value minus my model value here. Remember, like this equation, that's like my observed value here. Like that would be like this value, yeah, minus my model value. So that would be here EI. That would be like another EI. Yeah. So that is like my observed value minus my model value, and I can my model value. I know that this is this linear model. So that's basically like this is negative. Like you can also look at this. Yeah. So that is my linear model with the slope and intercept. So basically, I'm trying to find what is the value of A0 and A1 that will minimize this function. I mean, can we do this? Can we find the value of this guy and this guy that will minimize this function? Yeah, we learned how to do this. Yes, remember when we did like a derivative and a derivative test, and then you basically like take the first derivative. Here we have like two variables. So you first take the derivative with respect to this guy and then equate it to 0, and then you take the derivative with respect to this guy, you equate it to 0, and that would be like, will give you like your critical point, and this critical point, that would be like your minimum, your local minimum. So basically, that's how you solve this problem. So like just using the chain rule and equating to 0 to find the minimum SR. So if you just like took the derivative of this equation, yeah, with respect to A0, so do you remember like you basically, so that is, you make this u is equal to this guy, and then you bring this guy here, so like you get this 2, then you take the derivative like here. Remember, like, then you will take the derivative of this guy with respect to A0. So the derivative of this guy with respect to A0 would be what? That's a constant, so that would be go away. That's a constant, so that will be go away, and that would be like -1, and that's where you get this 1 here, and then time like your whatever, because like remember, like this 2 will be down, and then here 2 minus 1, and then you get this to the power 1. And then you equate this to 0, and then you do the same. You take the derivative with respect to A1, so with respect to A1, again, like you bring the 2 here, and then that would be equal to 0, that would be equal to 0, and that would be negative A1. So basically, that would be sorry, that would be not negative A1, like you're taking with respect to A1, that would be negative X, yeah? So you got like the negative out and the 2 here, and that like you have like this X here. So you equate this to 0, you solve these two equations simultaneously, and you arrange some term, and then you will get an equation for A1 that looks something like this, and for A2 that looks something like this. Basically, this means like this bar means the mean value of your Y value, and this X means the mean value of your X value. And this is just the number of data point xi, the sum of your xi times yi, negative the sum of your xi times the sum of your yi divided by n time your xi square negative x sum of xi and square, something like this. Yeah. So basically, we now we can solve this problem analytically. We don't even need to use any optimization like numeric solver or anything. We can just solve it analytically, and we have an equation that will give me like what's my A1 and what is my A0. Can we do this? Let's do an example, yeah? So here I'm just telling you these are the mean of X and Y respectively. So here is an example like this is a very simple example. uh, I'm giving you like this data. So this is like my uh, independent variable, and this is my dependent variable. That could be anything. Yeah, that could be, I don't know, like total nitrogen and harmful algae plume, or that could be water contamination, and that would be like house price. Yeah, that could be anything like your dependent variables. That's not important now. Let's. What's important now is to how to solve it. So can we solve this? Yes, we can solve. We have an equation for to find A1. We have an equation to find like the this guy, and then we can so this we find the intercept, this we find the slope, and that's very simple. So what is n here? N is equal to 3 because we only have 3 data points, 3 samples. We only took 3 samples. So n is equal to 3, and then basically you just sum xi times yi. So xi times yi, that's like 1 times 2, that's 2. 2 times 3, that's 6. 3 times 5, that's 15. You sum them, you get like 23. Then you got like x sum of xi. Xi is 1 plus 2 plus 3, that will give you 6. The sum of yi, 2 plus 3 plus 5, that will give you 10. The sum of xi squared, so 1 is, that's 1, 2, that's 4, that's like 9, so that's 14. You just do this term. Like this guy is square, so 6 squares, that's like 36. And then you basically like you have all your term, you substitute them here, and then you will get A1 is equal. So if I did all this arithmetic correct, hopefully I did this correct, then I will get A1 is equal to 1.5. So the slope basically is 1.5. And now can I get like the mean of my xi? So the mean basically is the sum over the number. So like you sum all these guys, that's 6 over the number, n is 3. So the mean of 1, 2, and 3 is 2. And you got like the mean of these guys, and that's basically the sum of the y and n. So the mean of the y is like 3.3. And if I substituted like the mean value here and this mean value here, and I know A1, then I know A1, and then I can solve for A0. Then I get A1, A0 is equal to 0.333. Yeah. So now I have the equation of my straight line. So my intercept is 0.0333, and my slope is 1.5. Now, can I, so this is my x value, yeah? This is my observed value, so this is the data that I collected, and this is my modeled value. Basically, like if I substituted 1 here, so that is like 1.5 plus 0.333, so that would be like 1.83. If I substituted my 2 here, like in my model, so that would be like 2 times 1.5, that is 3 plus 0.333, then you get 3.333. Then I substitute x is equal to 3, so that's 4.5 plus this guy, you get something like this. So this is what I'm observing, and this is what my model is telling me. So can I calculate the residual? Remember, what is the residual, or like the error? That is like your y observed minus your y model. And if I want to calculate the residual square, that would be like you square them, and then like you sum them. So like you square this guy, you square this guy, you square this guy, and you sum all of them. That would give you the SR, or the sum of the squared residual. Yeah. Let's see how we are doing in timing. We are doing not bad in timing. So basically here, these are like my observations. This is my model. So here, these are my observed points. Like at 1, we have 2. At 2, we have 3. And at 3, we have 5. And this is my model. And that would be my residual. So basically, like your residual, like what you observed minus your model, that would be your residual. Then you square it, then you get the residual square. Similarly here, This is what is this, that like I have like a negative residual here, which is like here I have a positive residual. For this guy here I have like a negative residual, and for this guy here I have a positive residual, because my model here is underestimating, my model here is overestimating, my model here is underestimating. Yeah, and then you square this, and then sum of the squared residual is basically like you take like you sum all this guy, and which is like what we did here, then you got like your sum of squared residual is 1.67. Okay, but here I'm not just showing the sum of the square residual, I'm showing something else. I'm showing like the r square of 0.96, which basically tell you that this model fits this data very well, or explains this data very well. Uh, uh, so what is this r square? What does this mean? So this is called the coefficient of determination, and let's just look at what this means. So like to understand like the coefficient of determination, R is proportional to the variance in the dependent variable that is explained by the independent variable in all variables if it's a multivariable linear regression in a regression model. So basically, uh, let's to understand this R, let's just look at something called like the total variation, or like spread around the mean. So like without like taking this slope line like here, I'm calculating this total variation. What is this total variation? This is like your R value, not with respect to like your regression line, but just with respect to like a line like to the mean value, which is like a line without a slope. Like if you have no trend, and that would be like the mean value of your y value of your observation, like this is just the mean value of the observation without any trend. So you got like this total variation. So you have some variation here. In that case, that is like a and you have some variation here, and then like you have some variation here. Now, uh, when you calculate this r square, what is this r square? Basically, this r square is 1 negative your SR, which is like the sum of your sum of the squared residual. It's basically like your the sum of the squared residual over ST. So basically uh, that is how you calculate the r square. So what does this mean? Like what does this equation mean, or how can you understand this? So r basically it is the portion of the total variant of the total variance in the dependent variable that is predictable from the independent variable in a regression model. So what does this mean? So like if we looked here, like to understand this, like you need to look at this figure. So the ST here, this represents the inherent variability in your independent variable. So that's basically the inherent variability in your independent in of your dependent variable without any trend. So if ST is large, what does this mean? This means that there is a lot of spread around like this, the y value around like this mean value, that will give you a very large ST. If ST is fixed and smaller, like you fix the ST and smaller R will result in higher R square. Yeah, so like you fix this guy, and like if this guy square is small, then this guy will be basically large. Yeah. So let's just look at like some of like the SR, or before we look at some of the limiting case, let's just also understand like what is the SR. So the SR, that represents the amount of variation that the model failed to explain. So basically this is the amount of variation here like this guy here, this guy that the model failed to explain. So if S is small, it means that the model fits the data very well. Like if this S, like this data is just right here on this line, this data is just right here on this line, this data is just right here on this line, this means that the model fits the data very well. If SR is 0, this means that like you have perfect fit, like perfect prediction. If SR uh, if SR, yeah, uh, is equal to your ST here, like you see, if your SR here, that's the important part, is equal to your ST, that would be equal to 1, and R squared would be equal to 0. What does this mean? This means that this model explains none of the variation, and us are and this is model does not cannot describe the variation or the variance of your dependent variable. So like the limiting case for R, like for a perfect fit, like if you have a perfect fit, the SR will be 0 and R will be equal to 1. So this regression model like perfectly fit all points on the data, and that would be like one of the limiting case. If no fit, if you don't have any fit, and basically like the slope of this line is equal to your mean value, then SR will be equal to ST and R squared will be equal to 0. This means that you have no fit and the regression line does not explain any variation in your data. This is just some, like this variation that you observe here in your data is just some random error or random fluctuation because your SR cannot basically is just equal to this guy. It cannot explain any of the variation. Uh, so that would be like the second limiting case. As SR approaches ST, then your R squared would approach 0. That's the summary of it. Like as SR approaches ST, your R squared will be 0. This means that you don't have a good model. Like your independent variable, your independent variable cannot explain your dependent variable. And as SR approaches 0, R squared will approach 1. This means like you have a perfect fit. So basically, that is how you could interpret this I value. Just for your information, like this is the equation of the models that I have here. And how did I calculate this? Basically, I calculated my ST, so you can calculate like this number here using the data that you have, and then if you divided like this SR by this ST and you subtract the -1, you get this, which is a very good fit. Which means that this model the portion of the variance in the dependent variable that's explained by the independent variable in the regression model. Okay, so let's just summarize this and see what R can tell us and what R cannot tell us. So for the general meaning of R squared, it measures the proportion of dependent variable variance explained by the model. It indicates how well the model fits overall, like the goodness of it. It does not tell you that the model is correct. Remember, I showed you, like in the previous example, for this sixth order polynomial, it has an R square of 0.999, but it's a wrong model. So it will not tell you that this model is correct. It will just tell you about the goodness of fit and how the variance explains the model. It will not tell you about causality. So it just tell you correlation. Correlation does not mean causality. Like I could find correlation. Two things are correlated, but not there is no causality between them. For example, like I could see like the temperature of the earth, like the temperature of the earth is increasing with time. I could find a very strong trend, very strong upward trend that like from every 10 decades the temperature of the earth is increasing with time. But there's no, does that mean causality? That doesn't mean that time causes temperature to increase. What causes temperature to increase is not time. What causes temperature to increase is another factor, which is the increase of greenhouse gases, not time. But here I just want to create a relationship between time and increase in temperature, whether this is a linear or non-linear, just to use it for prediction purpose or just to prove or to show that the Earth's temperature is rising. But it doesn't tell you about causality. It does not ensure individual predictors are statistically significant. Again, the same example, like the rising of the temperature of the Earth. Temperature of the Earth could be rising with time, but it does not show you whether there is a significant or statistical, like for example, like there is like harmful algae plume are increasing with nutrient, total nitrogen, for example. That is not like, and you get a perfect fit, like 0.99, for example. That is not a statistical significance. That is not a statistical, that does not tell you a statistical significance that like a b-value, for example. So statistical significance, that would be a b-value which suggests that the variable is statistically significant, meaning that like uh, so it does not like tell you statistical significance. Like you have to do like some statistical significance to complement like your R square. So in linear regression, it effectively show you how the linear relation is captured. If the linear regression assumptions are satisfied, adjusted R square account for multiple number of predictable, helping to mitigate overfitting concern. So adjustable R square, that if you have multivariable regression and you have, that is like not just like more complex model, like a model not with just one variable but two or three or four, so it's more complex model. So you adjust, basically you account for model complexity and you penalize the model for its complexity, and that will help you to compare between different models. It does not guarantee that the linear model is the best choice or detect nonlinearity pattern. So it will not tell you that the linear model is the best choice. To know whether the linear model is the best choice, you have to do other tests. And some of these tests, for example, as I told you, you can do like Bayesian model evidence, or you can just plot your data and see like how your data fluctuate, or you can check any nonlinearity in your data and so on and so forth. So for nonlinear regression, you can use still R square, like statistical software will give you the R square, but you have to use it with a grain of salt. It's a rough idea. It provides a rough idea on the goodness of it, but can be misleading for complex model. Like for if you have a complex model with like like many parameters and like high nonlinearity, this could be like your R square could be misleading and might not be used. And for comparison, like uh, via like R alone can be unreliable, and we usually additional metric, as I told you, like this IC method, like information criterion method, or Bayesian model evidence or something. Uh, Now here is what you need to pay attention. Higher R square does not mean that this is a good model, and low R square does not always mean that this is a bad model. And I showed you an example like where like for two models, the linear and like the null and the 6-degree polynomial, that has a higher R square, but that doesn't mean it's a good model. And the ones like the other one has a lower R squares, that doesn't mean that it was a bad model. But this is the most important thing. All these numbers, you have to interpret them, and all these model selection and all this relationship you build, you have to build and make all this decision by your domain knowledge, and by doing significant tests, and by doing other fit metrics like Bayesian model evidence or these guys for complete evaluation. So in some fields, for example, like I could have a relationship, like in some fields, that's field specific. Like in some field, I could have a model, for example, like this is my data. I have a model like this with an R square of 0.6. That could be like in some field, depending on your application, that could be an excellent model. In other field, for example, I could have like a very tight data and like my R is like 0.9, and that might not be considered like well or very well, like a good model. So you have that's like you have to basically look at your domain knowledge, understand your problem well, and don't just use this number blindly. Okay, so now last thing I want to do here, let me just go through multivariable linear regression. So like you can predict, for example, the selling price of a house based on several features. So square footage, for example, the number of bedrooms, and the age of the house. Yeah, so that could be uh, these feature could predict like the sales price of a house. So the hypothesis is that selling the price can be modeled as a linear combination of these features. So basically the price would be like this is my x1, that's be like my x2, and that's like my x3, and that's like here my a1, a2, a or b1 or whatever a1, it doesn't matter. B, I mean, I'm not like very rigorous in using this notation. Like if you are read this in a statistical book, they are very rigorous in using this notation. Here, I'm not really rigorous in using them. Like this E or like you use like E or like you use an epsilon. Like what's the difference between this E and epsilon and all this? Like you need to read this in a statistics book to understand. But again, this is not really a statistics class. This is just to give you more like a modeling class rather than a statistics class. Okay. Plus NE here. Okay. So you develop a multilinear regression model to predict the house price. So this is my data, for example, like with the square footage. So as the square footage increase, the price increase. The number of the bedroom, as the number of the bedroom increase, the price increase. This is the age of the house. You find like, I mean, newer house are slightly more expensive than older house. Like you see slight trend, but it's more like a random thing because it could depend on several factors other than these like locations and so on and so forth. So here I was able to fit a linear regression. So basically, so let's say like this is my x1, my first variable, this is my x2, this is my x3, and then here I was able to fit like this will be my first parameter, my second parameter, my third parameter, and my intercept here. Okay, this is, and like my R squares that I got was this, which means that like these variables, like this guy and this guy and this guy, can explain like big part my uh, of my dependent variable, which is the house price. Like, how did I solve this one? Actually, I solved this one like just as I would solve like a machine learning model, because I told you this is like a type of a machine learning model. Linear regression, whether like single or multi-parameter. That's a type of machine learning model. So I use one of Python library StatMod, and basically, so I have a training. I have like some training data that I train my model on, and then I got this modeling equation. Okay. I mean, this is if you are curious how I generated this data. So this is the model that I use to generate this random data. This is the model here that I use to generate this them data. This is the model that I use. I use like a beta function here to generate this data. And what is the true model for this? I use a true model. So that's the true model. That is the true model that I use to generate this equation here. Yeah. That's the true model that I use to generate, I mean, not this equation, this data here, the data, the underlying data. And this is the model that I was able to predict from this data, the models that I was able to fit to this data, giving the large error of this data. Okay, so now let's do one more topic before I will go very quickly over it. So for your linear regression model to be valid and to give you meaningful result, it has some assumptions that needs to be satisfied. So these assumptions are like linearity, homoscedasticity means like the variance is constant, it does not increase with your independent value. Uh, is normally normality, the error your residual is normally distributed or close to normal distributed, and independence like your uh, dependent variable, they are independent, they don't uh, have a structure in it or autocorrelation in it. So linearity, relation between x and y is linear. Independence, observation are independent of one another. Homoscedasticity, constant variance of error across all levels of x, and normality, residual should be approximately normally distributed. So here, let's just see I will not go into like what are the implication of violating this principle, because that could be like I could speak for hours about this. But I will give you some reference at the end, like to see like what are the implication of violating these assumption, and how could you relax these assumption in your error model. Like how can you account this so that your results when you use the least square method will be meaningful. So this is a linearity violation. So here, this is my data. I'm fitting a linear model to it, but is this a linear data? Well, how could I check for linearity? So if you plotted your residual, if that was a linear data, your residual should be randomly distributed. But you see here, it is not the case, because like what you see here, that what like you see here is that actually like what you can see here is that the model is somehow uh, I don't know, like it's not really like random. Like you have something here, it goes, it looks like this. Yeah, that's basically how your errors look like. So this means that like maybe this model, like using a linear model, was not like the best model like for fitting this data, or the underlying processes for this data is not linear. And this is true because I generated this data using this equation, using a nonlinear equation with a huge variance. So that's how I generated this data with a nonlinear equation. And then when you residual plot, you will see that like your linearity assumption is violated, because you don't see like these numbers are just not random, but like you see there's kind of a structure here. Okay. Homoscedasticity means like your variance is not increasing with your independent variable. So you see here, I mean, even without plotting any of the residual, by just looking at this, you see like it looks something like this. Like, see your like your data looks something like this. Yeah, it's not constant. It does not look something like this. It looks something like this. So if you plotted the residual, you will exactly see this. So you plot the residual. So here on the y-axis, this is like your residual EI, and you see like how your residual is just like how the variance residual plot, how the variance of the residual is just like increase as you increase x. So like here you have very small variation, here the variation is larger, here is larger, and here you have like a very huge variation. Yeah. So that is, so make sure that is here's this is accounted for. If it's not accounted for, there are ways like in your error model where you can handle this. I'm not covering this. I will show you a reference at the end if you want to look at these details. Now, finally, the normality of the error. So this is my data, yeah. And how could I know like about the normality of the error if my residuals are normally distributed or not? So what we to do this, we generally do something called like QQ plot of non-normal residual. So this is my sample quantiles, and this is the theoretical quantile. So if my sample quantiles fall on this line, like if these guys fall on this line, yeah, then my residual are normally distributed. If they don't fall on this line, this means that they are not normally distribution, and the normal distribution assumption, which is the main assumption for the least square method, is not valid, and then you have to account for this. Yeah. Uh, Was this data even like normal data? No, because see, like this error here, I sampled this from an exponential model. That's how I sample. I didn't sample it from a normal distribution, and that's why my residual are not normal distribution, because I didn't even sample it from a normal distribution. I just sample it from this exponential model. Yeah. And so I have a linear data, but like the model is linear, but the error is not normally distributed. The error is from an exponential model. Now, finally, is like the independence assumption. So we looked at normality assumptions, independence assumption. So that is so you see here is the data. That is like the data, and you see like the data seems like it is really not independent. There is kind of like autocorrelation to it, or like type of correlation to it. And to check this, like we usually do something called the Durpine-Watson statistics, and the Durpine-Watson statistics. So if this value is close to 2, that will indicate like no autocorrelation. If this value is below 2, suggests some positive autocorrelation, and if this value is above 2, that would suggest a negative correlation. So basically, like to detect for autocorrelation, you can do this Durbine-Watson statistic test, and you can even like here see like your residuals, see how they are very well correlated. Like you can, it's not really like they don't like follow a normal processes, but there are some underlying structure here. And how could I remove this structure? Well, there are two ways. You can remove this structure from your error model, like your E here, you can remove it, or just improve your model. Like this autocorrelation means that like this linear model is not really the best model that you can use. You don't need like for this process, you can improve this linear model, like so like your linear models that you used here is not the whatever this like linear model. I didn't show the equation for it, like whatever the slope or whatever, that might not be the best model to use, and you can try to change your model, like improve your model. Yeah, and that's how you could get rid of this auto correlation uh, your residuals. Yeah, you get like this autocorrelation of the residual shoes. That's like basically like you don't need to know this like in detail. I just like this basically. You might not understand everything I'm saying here. I'm going too fast, but this is just like mainly for your information, so you just become aware of these topics. And let me show you like at the end, if you want at the end, like in the bibliography, you'll find the reference if you want to learn more about like these assumptions, and if this assumption were violated, like how can you deal with them. So that's all for this video, and in the next video we will just whatever we learned we will apply to a linear regression problem. Okay, so